Hello everyone. This is a Raspberry Pi single-board computer from 2017. This is a single-board computer with tech from the 1970s. And today we're going to control the Raspberry Pi with the 6502 CPU design from 1975. We're going to do it over serial, but without the adapter. This is the 6501. It's a friendly little single-board computer, and it has a retro twist you might have gleaned from the relatively large dip chips that I just barely managed to fit on the Arduino Uno clone footprint. It's got a CPU with a 6502 core design from the 1970s, along with all the needed support chips. I made it to give the world a close-to-the-metal way of learning assembly programming and embedded development concepts in a fun and cheap way in 2023. I ended up with a useful piece of gear we can use for real-world things with our newfound skills afterwards. It's not a product I'm trying to sell, but since it's completely open source hardware and software, you can easily send off the design files to a manufacturer of your choice and quickly get a PCB back. You can even have the whole thing manufactured. You can put it together on a single standard size breadboard and follow along without ever having to smell molten solder. If this is the first time you hear about the 6501, I suggest you pause the video and check out some of my other videos where I show how it's possible to get a whole computer to fit on a single breadboard. I demonstrate how we can control I2C devices with the ancient 6502 CPU, and also how we can use that to control a common OLED screen with assembly code from scratch. And we even go through how to make a serial bootloader program we can use to upload code to the board, almost like a normal Uno. So if you missed all that, now is a great time to catch up. Don't worry, I'll wait. All caught up? Amazing. Let's get going. In this video, we'll continue a pretty deep dive into how the OLED screen works at the bit level and continuing to build the 6502 assembly code library for the SSD1306 and exploring how some things aren't always completely obvious from reading a datasheet. Coincidentally, we'll also be spending a bit of time exploring what ASCII terminal control characters are and what exactly happens when you press Ctrl+G in a terminal session. In the last video on this subject, I skipped a few things and instead decided to power through and make a serial bootloader and hack some ROMs. But enough procrastinating, let's get this done. As a sharp commenter remarked, how can we send an enter key or go to a new line if we didn't write the code to handle control characters? Well, we can't. Since the SSD1306 doesn't allow reading back the cursor position from any of the serial modes, SPY and I2C specifically, and since we can't really modify the module, or maybe we could, but we certainly don't want to, so we could use the parallel modes, we're a little bit stuck. And that's why I snuck in two videos between this one and the last one about the display. If we don't know where we are on the screen, it's not easy to know where to jump to when we get a control character like Newline or Backspace. That certainly explains why most of the Arduino libraries use a local frame buffer, but once again, that's 8 times as much RAM as we have in the whole system. Of course, there's also the fact that the display only lets us update a minimum of 1 column of 8 vertical pixels at a time, and if we only want to update 1 pixel, we need to know what the other 7 are, not to overwrite them. And without a frame buffer we can actually read, that's not going to work. But what we can do is to keep track of where we are on screen every time we update it. We could keep track of the current page and column in an X and a Y variable, but since we're currently only writing whole characters, we can actually make the whole thing way more efficient by keeping everything in a single variable. Let me explain. Since each line consists of 16 characters and we only have 8 lines, that means we can number each 8x8 pixel box from 0 to 127 in a single byte of memory, and with a tiny bit of math at opportune places in the code, we can easily calculate and change the cursor position really efficiently. So let's find a memory location for our new cursor and get going. To avoid moving things around too much, I'll move timer 2 to the string pointer location, since we won't be using both at the same time and they're always initialized. We could probably find other RAM locations to share, but for now we have a spot for our cursor position. Since we're using the send character routine every time we write characters to the screen, that's probably a good place to start. First, let's consider what happens when we receive a Newline character, like when we press the Enter key. Let's imagine we're already keeping track of the cursor position. What we want to do is go to the next line no matter where we are, and since the display can only reset its cursor location in absolute terms, we need to get the current line and add 1. If we look closely at our 0 to 127 cursor position variable, we'll realize that the first 4 bits are the location on each line from 0 to 15, and the next 3 bits hold the current line from 0 to 7. And if the 8th bit is set, then we wrap around to 0. That means the cost of having both line and character in the same byte is that we have to shift right 4 times to ignore the character position and just get the line. Luckily, a shift right operation of the accumulator only takes 2 cycles each. After that, we need to increment the line number to go to the next line. Maybe there's a point in keeping the line in the Y register, but probably not, so we can just increment the accumulator. There's actually no increment accumulator instruction on the 6502, but that makes total sense since an immediate add with carry only takes 2 cycles, just like the increment Y and X instructions. So adding extra circuitry for an increment accumulator instruction would have been redundant unless it could have been done in a single cycle. And it probably couldn't. So we just add 1 to the accumulator. After that, we want to make sure we're trying to set a valid line. And conveniently, we can do that by ending with 7, since that'll limit our result to the first 3 bits and roll over 8 to 0. Now that we have the line number that we want to set the cursor to, and the display has a command that'll do just that, we just need to send that command over I2C. Since we might want to use that in other contexts, let's put that in a subroutine. First, we save the line on the stack, save the I2C address, and start the transaction. After that, we need to send a control byte with the command bit clear, and then send the command from the datasheet. After the command byte, we need to send the page, so we grab that from the stack and send that. But wait a minute. Most of this is actually generic code to send any command, so let's put that in a subroutine too. Of course, that also means we can't hardcode the command, so we just put that on the stack. We need the line number twice because we also have to send the new end page, so let's put that in xtemp instead of on the stack. That way we can decrement it in memory to load it as the end page. Even though we already checked if the start page overflowed to the line number 8, we also have to check the end page since it might have underflowed to 255. And in that case, it should be 7. We just use the same trick as before and end it with 7, which will keep it in the range of 0 to 7. Going back to the Newline routine, we should also update the cursor position variable to our new line. Since we're changing the line before shifting out the character position bits, we add 16 characters to go 1 line down, and in case we rolled over, we end it with 127, so we restart at the top. And then we just save the new cursor position. I guess now might be a good time to test the new code. Even though we wrote a serial bootloader for sending a little bit of software over serial, we still can't update the ROM via serial. And since we're updating core functionality, we still need to burn the ROM again. Lucky for me though, we hacked this much faster flash chip to work in the 6501 in the last video, so I don't have to wait a whole 30 seconds for a single programming cycle any longer. It looks like I did manage to bend a pin though, so I better straighten that out if we want this to work. So it didn't really make sense to write the new subroutine in userland and send them via serial, but it's going to be a lot easier to test what our new code does using the bootloader. Let's just replace the current userland code with something that prints the letter A followed by a Newline character and the letter B. Then we just put the 6501 into bootloader mode and send the new code. Oh, it looks like I messed up a bit since it's only printing the letter A. You might not expect it to fill the whole screen like this, but since it's writing the character and then just changing the line, the character or column position doesn't reset like when you press the Enter key on your keyboard. So every time we print a letter, we're incrementing the cursor horizontally on the screen, and when we send the Newline character, we're only changing the line number. And if you look at an ASCII table, you'll notice there's a separate control character for both Newline and carriage return. Kind of like you'd expect from a typewriter, where changing the line and returning the carriage position to 0 would be two physically different actions. On computers though, the operating system determines whether pressing the Enter key sends Newline, like on modern macOS and Linux, or sends carriage return, like on a Commodore 64 or Apple II, or sends both Newline and carriage return, like on DOS and Windows. Let's quickly fix my mistake and send the code over via serial. To make what happens a bit more obvious, let's just halt the CPU in an infinite jump after our userland code. It looks like I forgot to call the send character routine, so with those tiny changes we should see something different. It kind of looks like something got the display stuck in what the datasheet calls page addressing mode. Perfect. We got the A character at the cursor position after the welcome message, since the clear screen routine ends up at the same place, and the B is printed the line below at the next character position. That's great, but not exactly very useful if we want to go to a new line and go to the beginning of the line. The feature we're missing here is a setcolumn routine, equivalent to the one we have for the lines. So let's go ahead and write that. Since it's a 3-byte command, just like the setPage command in our setLine routine, we can do the same thing. We save the column in xtemp, send out the command from the datasheet, grab the column, send it out, decrement it, so the end column will always be the position before the start column, and end it with 127 so we don't accidentally set the end column to 255. That should do the trick. So if we add that to our Newline routine with a 0 on the accumulator, that should act as a carriage return. If we ever receive a carriage return control character though, we should probably ignore that. Since we have to burn the ROM anyway, there's a little thing I've been wanting to do. Let's make it so if we're in text mode, which is the default at reset, and we get a byte containing a binary 1, we switch to bootloader mode. In ASCII, that would equate to the start of heading control character, which in the olden days actually used to have the same purpose, to tell the recipient that binary data or address is on the way. The reason we're adding it here is that we don't want to press buttons every time we want to upload code. Since we don't want to open a serial terminal to send the message, we can just add it to the assemble.sh script, using the same trick as before, using the echo command. There's the little detail that we need the delay to make sure the serial buffer has timed out before we start sending the code. We can probably add more serial control characters later. But first, we have to burn the ROM, of course. I should probably make it a little bit easier to change between burning ROM or uploading via serial with an if statement or something, but let's see what this does first. After updating the ROM, I assume we can just send the command via serial, so let's see. Yes, it works! It's a little hard to see though, since we don't clear the screen first, so we should probably do that when switching modes. But more importantly, our setcolumn routine works and our B is now at the beginning of the next line. Let's also put the A at the beginning of the line and see what happens. Oh, it looks like the display is in a weird state after resetting. I wonder what that's about. But at least the code still ran and did almost what we wanted. It looks like we got an extra line change we didn't ask for. Let's add another line change and see if we get 1 or 2 more line changes. Okay, just 1. Maybe it's the cursor position that's off. The serial bootloader is really starting to pay off, as we can literally get new code running in a second. If I add some more letters, it looks like it's just the first time we make a new line, we don't get what we expect. It looks like I forgot to put the end line in the output variable, so that might be a problem. But it looks like that did absolutely nothing to our bug. Well, we can start by fixing a few things that we know aren't working to our advantage. Let's make sure we set the line on reset and fix it so we clear the screen when loading code. Hopefully that does something good for us. At least the screen clears, but the loaded message still starts at a funny cursor position. Fine for now. But we still have the bug. Let's take a look at the Newline routine. It looks like we're keeping the character position when checking the range. This would actually be a good place to throw away the 4 lower bits that contain the horizontal position to reset it to 0. So let's end that with 70 hex instead. I'm not completely convinced that was the issue, but it does make more sense this way. That wasn't enough by itself, but maybe it's just that the cursor variable doesn't match the display cursor position. We can just clear the cursor position in the userland code. Ah, that actually worked. Things are a little bit more complicated without a local frame buffer, but so far I'm happy we can do so much with so little. Let's see if we can put each letter in the 4 corners by manipulating the cursor. Since we don't have an XY position routine, we'll have to change the line and column each time. That means we have to put the letters at cursor position 0, 15, 112, and 127. But that doesn't really seem to work. It looks like the first letter on each line prints fine, so maybe something's up with the setcolumn routine. Ah, that's certainly a problem. I forgot we're only sending the subroutine a character position from 0 to 15, but the display expects a column from 0 to 127. That means we need to multiply each character position by 8, and since shifting left multiplies by 2, we just multiply by 2, by 2, by 2. Let's burn the ROM again and see if that doesn't fix it. Nope, that just moved the glitch to the right side of the display instead. While we think about that, we might as well fix some of the other bugs. We should also clear the position before we print the loaded message, and maybe it doesn't make much sense to wait for a button press. Let's just delay for a second after we load the code. That way we can upload and run code without even touching the 65 Arduino. But I just broke the ground pin on the ROM. Luckily, I have another one of these hacked ROMs I can use, and then I can fix this one later. Or so I thought. My backup here looks like it has a pull-up resistor on the right enable pin that's not connected at all. We could also fall back to one of the old ROMs that take 30 seconds to program, but in that time I'll probably have this fixed. Time to fire up the soldering iron before we move on anyway. You can either be super careful you never break anything at all, or you can learn how to solder. I certainly prefer the latter. And since the iron's already hot, I might as well fix the other one. As you might have seen in one of my YouTube shorts, my go-to is to simply steal a leg from an LED since they're pretty sturdy, are easy to solder, and fit in most sockets perfectly. And of course you can still use the LED with the shorter legs. Okay, 2 chips fixed, but of course that did nothing to the problem at hand. It's time to really take advantage of the bootloader. I'm guessing the problem is with the setcolumn routine, so let's grab that and put it in the userland section so we can quickly test what's going on. It kind of looks like we're setting the right start column, but the end column is completely wrong for some reason. So let's see what happens if we hard-code it to 127. Okay, we now have a B in the top right corner, so that seems to do something right. Maybe my assumptions about what the setcolumn command for the SSD1306 does are just completely off. Maybe it actually can't wrap around if we set the end address lower than the start address. And then we just stuck on a single column until we reset it to something reasonable. Yeah, if we set it to 119 manually, we have the same issue. So assuming the column would wrap around and increase until it hit the end was just wrong. Since changing the column start and end is the only way we have to set the cursor position, this complicates things a bit more. I'm not sure there's an easy way out of that. Maybe we just have to add a bunch more checks and reset the column more often. I'd like to make uploading code even easier, so let's make a flag to decide if we're burning to ROM or uploading via serial. That way, we can just change that instead of commenting lines. I'd also like to suppress the messages we get when using kill all, so let's just grab the process ID and kill that specifically and use the wait command to suppress the message. No reason to have noise in the log. Now that we know the column doesn't wrap around, we might as well hardcode the max value for the setcolumn routine in ROM. And since we don't need to reuse the temp value, we might as well just use the stack. Instead of halting the CPU after running our userland code, we might as well just return to the main loop in programming mode. That way we can keep uploading code without touching the 65 we know at all, unless we need to update the ROM. Okay, now that we know how to put a letter in each corner of the screen, we can move on to other things. Like, does it work when we hit the enter key via serial? Since we're not setting the column when we reset the CPU, the display is still stuck using the last character column after reset. But we can fix that with a set column in userland. I should probably also add a page and column reset when we reset the board, as well as when we clear the screen. Now let's see if we can finally use our new cursor setting skills to press the enter key and go to the beginning of the next line. Does this work? You can't see it, but I just pressed the enter key twice, and no enter key, no new line. But let's see if we can find out why we're still not getting the new line we expect. We could start troubleshooting the serial connection, the terminal program and all that, but since we now have easy access to reading everything that goes through the serial port byte for byte, let's just try that. Since we already have the routines we need in ROM, it's a simple matter of waiting for the serial RX line to go low, read the byte, and print it on screen with the print byte routine we stole from my 6502 single board computer R1 code a little while ago. Pretty cool we can get code like this running in just around a minute in real time. Now we just open a serial connection and check what we get when hitting the enter key. 0D hex. I guess I shouldn't have made the code ignore the carriage returns, because for some reason that's what my terminal window is sending via serial. What's going on with that, you might say? Because didn't I just say modern macOS and Linux uses Newline and doesn't use carriage return at all? Well, yes. If we write a quick text file and check the output with XXD, we'll only see 0A hex for a line change, and not a single carriage return. So what's up? Well, the way the new screen command uses the serial connection is configured by the STTY command, or set TeleTYpe writer. If we take a look at the man page, we'll notice it has a few flags for determining how carriage return and Newline is treated. And if we take a look at my configuration here, it looks like I have flags set which convert Newline to carriage return. So I'd say the mystery is solved. Since I don't know if that's the default behavior for screen or macOS or whatever you're using, I'll change the code to accept carriage return as the line change character. Maybe you can tell me what default STTY output flags you see on your device with the STTY-A command. On Windows, I also wonder if PuTTY uses both carriage return and Newline as a default for serial. Let's flash the ROM and see where we are. Now, does it work? Where did the D go? Something isn't quite right. Every time I press the enter key, we lose the first character of the line. And it looks like somehow the line number stops increasing. Not good. Oh, of course. We figured out that if the end column was lower than the start column, we'd be stuck on the same column. That must be the same problem here. We're stuck on the same page because the end page is lower than the start page. I really thought it would just roll over, but I guess the datasheet made no such promises. What that means is we have to make sure we always set the end page to the maximum of 7. It also means we have to keep track of when the cursor position rolls over to 0 and reset the page when that happens. The way we do that is, instead of just incrementing the cursor on each character, we load it, add 1, end it with 127 to roll over to 0, and store it. That way we can branch on the 0 flag and reset the page. Okay, we're still missing the first character for some reason, but other than that, it's almost working, I guess. Maybe we should also reset the column, but if the cursor count is correct, that shouldn't really be necessary. After messing a bit with it for about 20 minutes, I noticed we didn't have a stop condition after printing a character and before resetting the line. So my best guess is we just ended up with a malformed I2C transaction after setting the line. Let's see if that does anything good. Moment of truth. Test and test. Aha, I think we caught the thing. Let's see about the page wrapping around. Does it work? Yes, it does. Yay! But it's not clearing the screen right after a page change. It looks like we have a working library for writing text and stuff to the 65 Arduino via serial. I think I'd like it to clear the screen when we wrap around though, and moving the setline and column routines also make our code a bit more compact. We'll find out if that works a little bit later. First, I'd like to try something though. You see, I'd also like to clear the screen when we send special characters via serial. Specifically, I'm a bit curious what characters we get when we press Ctrl+C. We can check that by using the same piece of code that dumps the hex value of a character again. So let's uncomment that. When we press Ctrl+C, we receive a byte with a value of 3 hex. Ctrl+C gives us a value of 1A hex, Ctrl+X is 1.8 hex, V is 1.6. I don't know about you, but I can't immediately see a pattern here. But if we take a look at character control codes on Wikipedia, we'll quickly see there is a pretty decent explanation for why we get a certain code for a specific key. It simply comes down to the ASCII representation of the character, but with bits 5 to 7 cleared. So let's say we want to figure out what byte we're sending out if we press Ctrl and the letter H, which is ASCII 48 hex. Well, we just end it with 1F hex to clear the top 3 bits. And that brings us to a byte value of 8, which would be the control character for Backspace. Now let's say we wanted to figure out what key we have to press to send the bell byte value of 7 hex. What do? We simply do the inverse from before and OR it with 40 hex, for instance. To set one of the bits we'd have cleared to get the control character, which means we end up at the letter G and we can press Ctrl+G to send the bell control code, which on a TeleTYpe would ring the bell. Now that we know how to type any of the specific control characters and why pressing Ctrl+H starts deleting characters, where were we? Yes, let's start by also accepting carriage return as a Newline character. Since we might want to delete some characters on the screen, let's also handle what happens when we press the backspace key, which, like we saw before, is either hex 8 or the delete key 7F hex. First, let's focus on changing the cursor position when we press backspace. So let's grab that. We don't want it to get lower than 0, so in that case we can branch on the 0 flag and return. Otherwise, we subtract 1 and save it. Now we need to make sure the display has the same cursor position. Since the lower 4 bits hold the column, we can throw away the line number by anding away the upper nibble with 0F hex, and then we just call the setcolumn routine. Since we threw away the line number, we grabbed the original value from the stack and shifted right 4 times to throw away the lower bits and send the 3 line bits to the setline routine. Since we might end up in a situation where the display column start address is set wrong when the line wraps, we also need to check that every time we increment the cursor position. Let's burn the ROM and test it. Now let's see what happens when we press backspace. Not much, except we change the cursor position. We still need to actually clear the character. Right now, it acts more like a left arrow key in overriding characters. Let's write the code to clear the position we want to erase. To do that, we need to send 8 blank columns and send the cursor position one more time. Since we're sending data bytes to the display, we start the I2C transaction by sending a byte with the data bit set. And then we just keep clocking out empty bytes. We could make that a lot more efficient by making a separate routine for sending null bytes, but that's a lot of work we don't really need to do, so this is fine. After clearing the character, we just need to resend the cursor position since the display incremented automatically when we cleared the character. Oh, and I goofed an optimization. We don't need to use the stack since the cursor memory location doesn't change, so we can just load it from there again. Now, if I didn't mess that up, we should have a backspace routine that successfully decrements the cursor position and also erases the character position we decremented to. With a few tests out of the way, it looks like that worked exactly the way it should. If we attach the keyboard to the 65 Arduino, I think we'd have a pretty decent serial terminal by now. I still wonder why screen on my computer doesn't actually delete the characters when it receives the erased character, but I'm not going to worry about that too much for now. If you know why, please let me know in a comment. Oh, and I completely forgot about something. Remember we actually went through the whole thing about control characters to figure out what happens when we press Ctrl+C, since I intended we could use that to clear the screen. If you're intimately familiar with terminals for some reason, you might be yelling at the screen telling me the erase screen sequence is actually escape bracket 2J, but to be honest, making this little board into a VT100 compatible terminal is a bit more work than I'm willing to put into this at the moment. So for now, I'm pretty happy if we just clear the screen when we receive a Ctrl+C, even if it isn't technically ANSI standard. Now let's see if it actually works. So if I burn the ROM and try it out, let's see what happens when I press Ctrl+C. Yay! Ctrl+C clears the screen. And does Backspace work? It certainly works like we'd expect, but like I mentioned before, it doesn't erase anything on the screen. Either way, here are my current STTY settings if you can figure it out. Now, why would I go through all this trouble of making a minimal 6502 computer into a 1960s computer terminal anyway? Well, bear with me. As I teased in the intro, we're going to control this Raspberry Pi 0W with the 65 Arduino. But what does that have to do with all the hoops we had to jump through to get the 65 Arduino to display text on a display? Well, usually after you grab a copy of Raspberry Pi OS, throw it on an SD card, you'd boot up the Pi with a screen and a keyboard attached and control it that way. Or if you didn't have a screen, keyboard, and adapters for that matter, you might connect to the shell via Wi-Fi and run it headless. But what if all you had was a terminal from the 60s or 70s and a MAX232 chip to convert RS-232 to TTL levels, and you really wanted to use that to control a Raspberry Pi? Well, that's basically what we've been getting ready to explore so far, and I think we're ready to give it a try. To get the Pi here to cooperate, you might think I'd have to jump through some more hoops, but what we're trying to do is actually a stock feature on the Pi. After downloading the Raspberry Pi OS Lite version, figuring out my card reader device, and writing the image to the SD card, I just have to create a user account, check the UART is enabled in config.txt, and lower the baud rate to 9600 baud from the default 150,200 in command line.txt. And the only part of that which was out of the ordinary was lowering the baud rate. We could just hook up the Pi straight to the 65 Arduino, but I'd like to add some more buttons for control anyway, so let's bring in a breadboard. To check things are working, I also put an LED on the same pin as the onboard LED, and for good measure I add a 100 microfarad capacitor to the power rail. The Pi is a 3-volt device, but its regulator doesn't mind being fed 5 volts from the outside on the 5-volt pins. The serial TX pin from the Pi we can hook up straight to the 65 Arduino, since the 6532 can still work with 3-volt logic. But hooking up a 5-volt output to the RX GPIO pin might let out the magic smoke, so let's feed that through a voltage divider. I grabbed 2 resistors at random, and they happened to be 22 and 47 kilo ohm, which hooked up like this with the 47K to ground will give the Pi RX a reasonable high-level voltage of about 3 volts, since the NMOS 6532 doesn't actually pull up all the way to 5 volts. And that should actually work, or at least do something. I also add the 2 buttons, which we can use to control things later. Note that I don't need to add pull-up resistors, since the NMOS inputs are already internally pulled high, which is kind of a nice feature. If I pull the power from the Pi while we power up the rest, we can clear the screen before we power up the Pi. Here we go. This is so exciting. Oh wow, it's actually working. Well, it's failing horribly and spitting out plenty of buffer overflow messages and misread serial data because of it, but it's actually receiving a bunch of kernel messages and the boot sequence is chugging along. We have the right baud rate, so we're receiving many characters correctly, but we're receiving more characters than we can handle, and when the RAM is full, there's nothing we can do but just to give up and dump what we have in the buffer to the screen. And that means we lose the characters coming in while we're writing to the screen. It also means we might start receiving again in the middle of a byte, getting framing errors and corrupting data until we get a break in the data stream. Since the Pi 0W here isn't the fastest of Linux machines, I've sped up the video quite a bit here, but eventually we should get to the login screen. Of course, we could just log into the Pi using the USB to serial adapter and a modern computer, but where's the fun in that when we can program the 65OE to do it without a modern computer around? That is the point of this video after all. For instance, we could use this method to gracefully restart a Pi without a computer around, and without just pulling the power, as that has been known to corrupt SD cards. And there it is! We are ready to log in to the ARM computer using our 6502 computer. But before we jump straight on that, I'd like to do a tiny bit of housekeeping and remove most of the serial echoes, since we really got a lot of framing errors from starting our serial reads from the middle of bytes after the buffer overflowed. The main problem is the speed of our current screen write routine. Since we're echoing out everything we receive via serial and printing it to the OLED screen, that means we need the same or more time to write characters to the screen and serial than just to receive, since our send and receive baud rates are the same, and we also have to write characters via I2C. To lose a few less characters, we just remove the default serial echoing. It would mean that nothing shows up in the screen terminal, but since we can just enable local echoing, we don't really need that. And of course, we still need to be able to write strings via serial, so we can just copy the SSD1306 string routine and change the send character call to the serial TX call. Since we don't waste all that time anymore, that should mean we lose less characters. It might be hard to see at this speed, but I think we are getting a lot fewer framing errors. Yay! Now let's write some code to finally do what we came for. Let's log in and control the Raspberry Pi using the 65OE. Basically, we just want to type our username Pi, followed by a new line, and then our password and another new line. Since we have the buttons hooked up to bit 6 and 7 of DRA, we can just use the bit instruction to check if a button was pressed. If the right button on bit 7 is pressed, the negative flag will clear, and if we press the left button on bit 6, the overflow flag will be clear. I have a hunch we can't just send the password immediately after the new line, so let's first send the username part with the right button we hooked up, and then use the other button to send the password. The way we set this up, we stop checking the right button after it's been pressed once, and then move on to check only the left button. Otherwise, we might send the username several times in a row. Since the code is in userland, we just need to send it via serial, so while uploading the code, I need to swap the wires so we don't just short the Pi's TX pin with the serial adapter. Then I just swap the wires back and press the right button to send the username, followed by the left button to send the password. We don't actually see the Pi asking for the password, since the userland code isn't set up to show the incoming serial data. But after we send the password, we actually get a successful login. We also get a buffer overflow, because even the login message is a bit too long. But that doesn't change the fact that we're now logged in and the Pi is ready to do the 65OE bidding. Let's make it do something simple first. Let's change the left button to list the root directory instead of sending the password. And that works. Of course, the cursor wraps around and the screen is cleared, so we miss a bunch of directories, but we can clearly see it did what we wanted. If we try that again, I bet we kind of get the same result. Yeah, it really would be nice if we could do some scrolling that didn't involve rewriting the whole screen. I think we can probably use the hardware scrolling feature of the SSD1306 to avoid clearing the screen, but I think that's a bit out of scope for this video. Let's see if we can do something that doesn't fill the screen. Listing the root home folder shouldn't do much. Permission denied. Should have used sudo. Since the example I used for why this would be useful in real life was a graceful restart, let's ask the Pi to power down with a sudo poweroff. If that works, we should see the Pi reaching that run level and the power LED turn off. And it did! Success! Our 6502 single board computer managed to control a modern Linux computer and made it shut down. Of course, we could now automate that and put it in ROM, but I think you get the point if you made it this far into the video. If you made it this far into the video, you might also want to hang out on the channel's free Discord server and chat about what you like about retro computers. Link in the pinned comment. And maybe you even want to become a member of the channel and give me some extra encouragement to make more of these videos. Either way, thanks for watching.